you need to Ah, sure. What this? Disconnected.
That's
Yes. No, I mean, like I said, whenever it comes, it goes very quickly too.
Okay. I forgot about it this morning. I did it. Nice.
Oh, never. Ready for fall break?
Yeah, 6, 7, 5 to go home.
Oh, where are you from again? Oh, that would be a bit of a trek anyway.
Yeah. The question is like, so.
Excited to. I honestly forgot it was fall break this week because I just like haven't been like I didn't.
Yeah, I get that. I think I'm more like, wait, why am I so burnt out? Like, why am I like struggling right now? Oops, yeah, that's right.
I'll do some of it today.
I like just remember we had homework like last night. When do you probably start that?
Yeah, per chance. Same with all my other classes.
Yes. It is, yes.
You're so real for that.
You're the first person to like recognize.
Seriously, that's crazy. What?
The sweatshirt.
Oh, it's so scary. How would you do that? Because I'm it's
You're asking.
They say, I think like you said.
You know? Oh, no, I have no idea, but in general, like last year it would take a while, like 2 weeks to expect.
Equations that.
We're not the ones who it's just him and there's so many students.
Yeah, wait, that's.
So it's kind of crazy.
That's crazy that
Yeah, no. Yeah. Like everyone who gives you homework is a grad student. But no, the grad student.
Yeah, exactly. Start from the same.
Yeah, by the time you get it back, you will have forgotten everything that was on the test.
That's always work is always
It's a fun challenge in the class.
I don't even remember when I was.
Yeah.
the spring force.
It's so different because now that I'm taking like biology and chemistry courses, they get it back like in 2 days.
I know my mom said it's like 1 day, like literally the next morning. She's like, "Oh yeah, it's like grades are."
Okay. All right. So, yeah. Back from the weekend. Just a week to go till fall break. Reminders. Last week we had off from quizzes and homework because of midterm. This week we're back on for quizzes and homework, so don't forget this homework due today. Yeah. Last time we were talking about work. We're going to continue with that and then move into energy more generally. Did we do this question?
Yeah.
In that case, let's start out with.
Yes.
This question. Yeah, go ahead and get your work papers out.
You can do. Okay, awesome. Yeah.
And something above our load. One more time. One more time. Ready. Okay, mostly for B is correct. So let's recap a little. So we said that work is integral f dot dr, where f and dr are both vectors, and it's taking it from some initial position to some final position. And we said that if the force is constant, which does apply in this case, then we can simplify this to f dot delta r, where delta r is the displacement. And they're both still vectors, and this is a dot product. So in this case, we would have had 3 newtons I hat minus 4 newtons J hat, dotted with, because it was 5 meters in the negative x direction, so that'd be minus 5 meters I hat. And what is I dot I? 1. And J dot I? 0, yeah. So dot product for perpendicular vectors is 0, and so we only get the I part, and so we get minus 15 Newton meters, but a Newton meter is also called a joule. All right. Question on this? No? Okay. What else did we learn about? We learned that there is the work energy theorem, which relates the total work done on a system to its change in kinetic energy. So it says work total is equal to delta K. That is K final minus K initial. So try this. We have a box resting on a floor, given an initial velocity. And friction slows the box down by exerting a force of 0.5 newtons on the box as it slides across the floor. And the friction of force slows it down until it comes to rest. And the question is for the distance the box slides. So obviously there are multiple ways you could solve this. You could solve it if you wanted using kinematics, but instead I want you to try using the work energy theorem and pay attention to the signs when we use it. Yeah. Don't try and do it in your head, grab a notebook, take it out. Oh, that is
Okay.
there we go. Right. We have the minus sign. Okay. People need more time? Bit more time, okay. Okay, going to. Okay. Alright. Okay, Liam, do you want to take us through your reasoning?
Yes, so we know that the initial, so we know that work total is going to equal the change in kinetic energy. We know that the final kinetic energy is 0.
Yes.
And we know that the initial kinetic energy is 10 kilograms times 5 squared meters per second times F, which is 125 joules. And we know that that is equal to 0.5 newtons times the displacement. So we can divide 125 by 0.5 and get 250 meters.
Okay, yes, you're correct. I do want to highlight one thing though. So yes, we have work total equals delta K. In this case, the force that is doing work is just the friction. If we drew a free body diagram. So if we drew a free body diagram of the object, we would have mg, we would have the normal force, and if we assume that it's moving to the right, then there would be a force of what kind of friction? Kinetic friction, yeah, because it's sliding. Yeah, to the left. So we have these three forces, but only friction is doing work because the other two. Why don't the other two do work? The perpendicular, or they're not on the axis of the motion. So we have work of friction is K final minus K initial. Exactly as Liam said, K final is 0, so we have minus K initial here. And the friction, at least for this duration, is a constant force, so we can do F dot delta R. Sorry about that. The thing I want to highlight is the minus sign. So on this side, we have the minus 1/2 mv initial squared. And where will the minus sign come in this side?
The displacement and the force oppose each other 180 degrees.
Exactly, yes. So this dot product, remember, takes into account the directions of the vectors, right? And in this case, there's a 180-degree angle between them. So you can either do it like, oh, magnitude of friction times the distance times cosine of the angle between them, or you can do like x components, and one of them is positive, one is negative. But yes, you get a minus sign because of this cosine 180 degrees over here. So you get minus F friction times D equals minus 1/2 mv initial squared, and the minuses cancel, and so you can get that. All right. Good. Thank you, Liam. So yeah, just wanted to emphasize that be careful with your signs when doing these problems. Okay, so let's try. Okay. Quick one, won't give you too long. Alright, and show me what's. Mostly for A is correct, it's positive work done. Now, pretty much the same question, I've just changed one word. You want to read one time? Alright, show me what you think. Less certain this time. Alright, go ahead and discuss.
I thought that was the first one.
Because I think it's not always, it's not always perpendicular to. Right, because tension is this one, so gravity is always pulling down, so it's always. Be zero if they.
It's just the separate force happening. So basically, the gravity's here in this case, and force is going that way.
Yeah, but like, it's not perfectly, it's not moving perfectly. So there is some, I know. I think you're right. Wait, yeah, because it was at least be perfect.
Yes.
Yeah.
Only three choices.
It's insufficient.
Right before you do the integral. Two. Well, some combination.
It's like really different direction of gravity. Like last time I did that, and then
Literally when you open
Okay. Get ready. All right, mostly for B is correct. We look at the angle between the force and the instantaneous displacement, but the instantaneous displacement is in the direction of the velocity. So if we look at F dot V, that would be magnitude of F times magnitude of V times cosine theta. And in this case, the force is the force of tension, which is along the string, and the velocity is tangential to the circle. And so the angle between them is 90 degrees. And so we get cosine of 90, which is 0, right? So what the tension does is it doesn't increase or decrease the kinetic energy, it simply redirects it, right? It changes its direction. Or you can say that it does equal amounts of positive and negative work, right? It is, you could say if you want that it is, I guess, slowing it down in the vertical direction, but speeding it up in the horizontal direction, right? But remember, at the end of the day, though, work is a scalar quantity, it doesn't have components, right? So we just look at the overall effect, and the overall effect is it doesn't change the kinetic energy. Questions? Yes.
So we will always be looking at the direction of velocity when we're trying to figure out whether work is positive or negative or what side.
Direction of velocity with respect to the force, as in the angle between them. Other questions? Okay. Actually, this quantity f dot v will show has another name. So we've seen work equals integral f dot dr.
Yes.
Oh, we have. Yeah, no worries. Yes. F dot dr. And so if we remember that this integral is basically a sort of sum of little contributions. So if we don't do the integral, we just have a little bit of work from a little bit of displacement. All right. And so yeah, so we have a little bit of work from a little bit of displacement. And so if we're interested in the rate of doing work, we can do dw dt, right? The rate of doing work, and that's f dot dr dt. Or what is dr dt? Velocity. So we get f dot v. And this is called power. Right? The rate of doing work. See? Yes.
If power is equal to like a dot product of something, how is it like a rate? Because isn't rate like blank, like over blank usually?
Yes, so this is work over time.
Oh, oh,
Other question? Yes.
Is power a vector or scalar?
Okay, good question. It's the result of a dot product. So it should be scalar, yes. The result of the dot product is a scalar. Yes. The units would be, we can figure out if work is measured in joules, then this would be in joules per second, right? So the unit of power is a watt, a WATT, a WATT, all right, after James Watt, who didn't invent but improved the steam engine. Unfortunately, the symbol for a watt is a capital W, so yeah, which is, you know, the symbol that we often use for work, which is not measured in watts. So be careful with that. Yeah. Okay. So let's see. All right. Yeah. So yep, we have this demo here. So I'm going to we have a sort of makeshift pendulum, heavy ball on a string. I'm going to lift it up to this level of the meter stick, 2 meter stick, and let it go. And the question is, it reaches the other side. Same height, lower height, equal height, higher height. Sorry, same, equal, the same. 3 choices. Okay, won't be too long on this. And Okay, pretty much, most people say, equal height, and that is correct. We can experimentally check. How's it gonna be good?
Yeah.
Okay. So hopefully it's about level. And so, yeah, goes there, at least for the first swing. And then slowly, because of losing energy at this connection point, it will slowly gets less and less. But the first swing, we didn't lose that much energy, so it swung up to the same level.
Is that because of air resistance or because of?
I mean, air resistance plays a role, and then also because it's not completely rigid over here, and so it's like bending it a little bit and loses some energy there. Yeah. All right, so now the next question is, what if I did the same thing, but in the process of the swing, I inserted this rod? Okay, so that once it swung past the halfway point, it would, wrap partially around this rod. So now, will it go to the same height or lower height or a higher height? Okay, so I'm going to put in a bar. Actually, you know what? Go ahead and discuss.
There's
Right, I thought it was like higher.
Potential energy from
We're great, yeah. What is the equation? It's like,
almost.
I feel like I do it. Yeah, like what is
It's one of those times when too much knowledge is burning.
I would say it's too much knowledge.
Yeah, like it'll split higher, like potentially the radius.
Okay, all right. I won't give you too long on this. Let's see what. All right, all three camps have representation in DC. Let's try it out. Actually, could I have Lauren, if you could hook me up? So then, which role do you want? Either the rod or the ball? The rod?
I feel like the rod is harder, but I don't.
Yeah, sure, go for it, yeah.
Do you want me to insert it right when you like let it go? No, after.
How about, no, that's fair, let's
How
decide.
about I do
exactly.
that? And then-
Okay. All right, so I'm going to let it do the first swing. No, actually, I'm going to insert it right on the first swing itself. Okay, so
Insert now.
that's actually true. Okay, we've already seen it without. All right, so go ahead. Oh, still goes to the same height. Thanks.
Guys, I rigged it.
Okay.
Is it supposed to?
Yes, it is supposed to do that. Yeah. So, what's going on? Nothing much. The only force that's doing work, we've seen, is gravity, right? We know the tension doesn't do work because it's perpendicular to the motion. And so, it's still the same force of gravity doing work, and so it still needs the same distance to do that work over. And so it needs to rise to the same height. Because gravity is only acting in the y direction, right? So it needs to have that same displacement in the y direction to fully nullify that.
Could you point to some equations that prove that back that up? Where should we look? Is this work? Is this kinetic energy? Is this?
Oh, okay. Let's talk about how we or also sort of what's special about gravity and a few other forces. So in this case, we would say work total equals delta K. And so the work here theoretically would be work of tension plus work of gravity equals delta K. But then we know that this is 0 because it's at 90 degrees. And so we have the work done by gravity is delta K. So we have to define which is our initial point and which is our final point. In order to avoid this side just being 0, well, we could either choose our initial point being the lowest point and our final point being like where does it come to a stop, or we could do it from rest to rest. But for clarity, let's do it. Our initial point is at the bottom. And our final point is when it stops for a moment. Right, so when it stops for a moment, the kinetic energy is 0, so we have 1/2 mv initial squared. And on this side, we have the work done by gravity. So I can write that as F gravity dot dr. What's the equation for the force of gravity? Mg. And what if I want it as a vector? Negative mgj hat. Well, I have a set of my axes, but yes, let's assume that upward is positive y. Yeah, right. So yes, so we would have minus mgj hat, right, dotted with er. And then this side is still the same, minus 1/2 and the initial. All right. Well, what did we say dr was? If we were to write it out, we said that this was it's like a lot of little displacements in different directions. It's a vector, so there'll be like an I, J, K. Small change in position, right? So if I move only in the x direction, what would I call that? I mean, the direction would be I hat, and if I want to talk about a small displacement, that would be. Yeah.
dx.
Dx, yes. So yeah, this is dx I hat plus.
Yeah.
Well, not dx anymore. dy, dy j hat. Yep. Plus dz k hat. Yes. All right. But now when I do this minus mg j hat dot dr, what is that going to give me?
Just
Yes.
Like all the ones that are not j hat will cancel out, so it'll be negative mg dy.
Yes, that is correct. Right. Or if you want to make it more explicit, we can put there's a j dot j here, but j dot j is 1. Right. And we know that j dot I is 0 and j dot k is 0. And so those will go away. So we just have this, and the j dot j is 1. So we just have minus mg dy. So now this step has become integral minus mg dy is equal to minus 1/2 m the initial squared. And what is my variable of integration now on this side? Y, right? Because the d is attached to the y. So that tells me that, oh, my integration bounds need to be in terms of y. So this would be from some y initial to some y final. Okay. M and G are constant, so I can pull them out. And we can take the bottom point of the swing to be at 0 height. So I'll make this from 0 to y final, dy. And then integral dy is just y. So I get minus mgy from y final and 0 being the bounds, with minus 1/2 and the initial squared. And so I get minus mg y final minus 0 equals minus 1/2 and the initial squared. And yeah, I can cancel out the m's if I want. I can solve for, cancel out the minuses, solve for y final, and I get v initial squared. So this is really v bottom squared over 2g. Because our initial point we said was at the bottom. So yeah, we see that, oh yeah, it doesn't depend on anything except the speed at the bottom, which is the same in both cases. Questions? Yes.
How did we get from like having an integral sign to like not having the integral sign?
We did the integral.
Okay.
Yeah, no, that's a fair question. Yeah, we integrated dy and got y. I know, if you haven't studied integration yet, then it's mysterious, but yes.
I have, I just forgot everything.
Other questions? Yes.
Why did we take the velocity at the bottom and not the velocity though? Oh, it would be zero when we.
Yeah, it would just be sort of 0 minus 0, so I wanted it to be sort of clear that we're starting with something non-zero. Other questions? Alright, so this is a sort of, let's sort of note a few key points in this procedure. We had work total equals delta K. We split up that work total into the work done by the various forces. We figured out, oh, some of the forces can be neglected because they don't do work. We figured out that the delta K could be simplified. And then we plugged in for the specific forces and we evaluated. And what we see is that because gravity only acts in the negative y direction, only displacement in the y direction is important. All right. So one thing you would have noticed is that, yeah, okay, I didn't have to make it 0 here, actually. I could have just made it y and kept it as y initial. Right, so let me just do that for a second. So then this would be like delta y. But what's interesting is that this expression for work only depends on where it started and where it ended. The fact that it was moving along a circular arc didn't matter, right? And this is something special about gravity. So if I take this piece of chalk from the floor and put it on the table, right? Gravity does a certain amount of work. But I could equally take it from here and do this, right? And gravity would still do the same amount of work, right? It only depends upon where I start and where I end. So these are a special class of forces where what we say is the work done is path independent, right? It only depends upon where your path starts and where it ends. And these are what we call conservative forces. And this is going to take us into conservation of energy and potential energy and so on. So conservative forces work done is path independent. Yes.
Does this have to do as well with like conservative vector fields and like?
Yes,
gravity?
yes, yeah. If you know about conservative vector fields, they have associated potential energies. Yes.
Yeah.
All right, so work done is path independent. This has a sort of immediate consequence. What if I take an object, move it through some path, and then bring it back to its starting point? Work done will be 0. Yes, that's right. Okay. So, yeah, if the work done in taking an object through a cycle and bringing it back to its starting configuration is 0, that's probably a clue that the force you're dealing with is a conservative force. We can ask, is friction a conservative force? I could take this box and move it around this table and bring it back to its starting point, is the work done zero by friction? No, it's always converting it into heat, right? Because the thing with gravity was if I do it in a closed circle, if I take gravity acting on an object for a closed cycle, what we see is that, when I'm lifting it up, gravity is doing what, positive or negative work? Negative work, but when I bring it down, it's doing positive work, right? So they cancel out and ends up being zero. With friction, because it's always pointing, the kinetic friction is always pointing in the direction opposite of the way it's moving, at least in this case, then that's always true. So it's always doing negative work and turning that into heat, and you don't get a recovery of energy at any point. Yes.
Would static friction do positive work though? Like if it's like in the same direction of.
Oh yeah, no, static friction and even kinetic friction in certain cases can do positive work, yes. But yeah, what we find is that they are not conserved. Yes.
And this delta y is also independent of like what the distance of this pendulum is, like. What does this then have to do with making the distance between of this rope so that it can swim back up to the same height? You know what I'm saying?
Not quite.
So this pendulum.
Yes.
We decided that it would swing back up to the same height, but I initially thought it would go higher.
Okay.
So how does that prove that is?
Oh, because what we showed was that the height that it gets to only depends upon the speed of the body.
Okay.
Yeah. Question? Anyone else? Questions? No? Okay. Let's see. All right, well, we'll do just a couple more work questions before we transition to potential energy. Yes, okay. So, screen down. Object, you have the mass, subjected to force, points in the positive x direction, object starts with initial speed, x equals 0. F is not constant. Function of position. It's already moving. Let's say this. Object starts with just as. Oh, fair point. Yes, we'll say for simplicity that it's moving in the positive x direction. Doesn't have to be technically, but yeah, let's say that it's moving in the positive x direction. You will need more time? Bit more time. All right. Ready. Okay. Go ahead and discuss. I will tell you that the answer is not C. So, but it starts with my thinking is basically it had when it struck it has torques. The initial combined with these integrals are always changing something. Changing like I was feeling like an area underneath one.
And then you know that it starts actually. So you provide.
That's what it normally is. Maybe like that.
It's 9:30.
Yeah.
And then the initial energy.
Okay, so
One
the
time.
final is
Which is like.
But do we need to factor in the
Initial energy.
those two sets together?
And the final energy.
Yeah, we were all.
Okay.
We find the area through that kind of. Okay.
All right, sounds like discussion's died down. Get ready, vote again. And show me what you think. Okay, fairly unanimous for E. E is correct, yes. Always remember that these area under the curve, like these integrals always give you the change in some quantity. So the change in kinetic energy is the area under the curve, or which is the work, which is 3 joules, but it starts out with 4 joules of kinetic energy, which we can figure out from the initial speed and the mass. And so we get 4 plus 3 is 7 joules of, is the final kinetic energy. All right. One last work problem. All right. Yeah, okay. Take your time, read that. I'll put it on the whiteboard also, maybe a bit more legible. Right, so same hockey puck in 3 different cases. We use the initial speed and final speed. Asking you to rank them according to the work done by the force that is acting on it. There's no friction. Oh, that seems to be. Okay, alright. Just realized that it says VI on this one, but no, I guess it's a very blurry F. Okay, alright. Okay. So, are you guys ready to vote? Yeah, alright, show me what you think. I'm seeing missing votes here, come on. Okay, okay. All right, I'll give you 1 minute to discuss.
I was like,
First, I was thinking, I thought it was more about.
So
And if you want to get squared, then it doesn't matter. Why not?
I mean, I think you are right, like,
So one of your names on the angle.
okay, yeah.
Oh, wait.
Yeah, like the arrow.
So we don't really know enough about the force changes.
Wait, so you can see.
So we were used to.
Okay.
Wait, so it's 5 squared minus 2 squared. 11 squared minus 10 squared, right? All the same. So, okay, so 11 squared minus 10 squared is 21. Yeah. 5 squared minus 2 squared is 21.
I didn't say mine would be
So like that, you know,
Sorry.
change in
yeah, that's true.
I figured out or you're probably making
Okay. You don't have that much time, so let's see what people think. Show me a moment. Okay, all right. A lot of people for F, but the right answer is E.
What?
I know, very counterintuitive, which is why I like this question. We don't know enough details about the force to do integral F dot dr, right? Because they just tell us the initial and the final. So we focus on the change in kinetic energy. Kinetic energy is a scalar. It doesn't care about which way it's heading. You just need the magnitude of the velocity. You need the speed. So if I do 1/2 mv squared, right? Here I would have 11 squared minus 10 squared, right? Which is 121 minus 100, so 21. Okay, same thing over here. And here you'd have 5 squared, 25, minus 2 squared, 4, which is also 21. And so all three of them give the same result. Now I'll end on one thing, because I know that intuitively it feels sort of wrong. It's like, how can this do the same work as this? Doesn't this have a complete change in direction? Okay. Here's the thing. Work can be both positive and negative. Okay. Here, all you have to do is speed it up. You just need to push it in the same direction. Here, you first need to slow it down to 0. During that process, you're doing negative work, but then you need to speed it up to 11. And that process, you're doing positive work. And when you combine those, the total amount of work done is the same as in this. All right, that's where we'll end today. Next time we follow up on potential enemies.
So you squared the velocity. You said 1/2 mv squared
Yes.
initial minus 1/2 mv squared final.
Other way around, but yes.
Sorry, and that simply gave you. Why are we not doing? We do the distance formula, that would be a speed.
Are you asking?
Like,
Why don't we do final minus radius then square?
No, why don't we do?
Components of what?
Practice the distance. Why are you doing speed and not the vector?
Oh, because we can change the kinetic energy, right? Formula of kinetic energy.
Actually, what you had it.
1/2 mv squared. And so that velocity is vector, but when you're doing the v squared there, what you're doing is v dot v. Which is the scalar dot. So in a sense, you are doing Pythagorean there, right? But it's buried in the vx squared plus vy squared plus vz squared. And you do that and then subtract.
I just wanted to ask if that only one midterm for this.
No, this is something else.
Yes.
Yeah, early November.
Thank you. The thing about work total is changing, so energy, energies.
Oh, then just send me a picture of your score and I'll update.
Okay, awesome, thank you very much.
So nice to have a class with these.
Oh yes, let me, first let me just add the previous